handout to you. The book that I copied this out of does a nice job motivating one of the properties that we like to talk about with determinants. Where does it come from? That the textbook that we use doesn't do, as my opinion, doesn't do as good of a job of motivating why we care about the determinant function. It will become more important with another application later in chapter 7. But I wanted to give a little bit of motivation as to where determinants come from. What kind of a thing are we trying to compute when we're talking about determinants? So the first thing that I need to do is talk a little bit and remind you about some vector things. So if I have a matrix, say I had the matrix 3, 1, -2, 5, say. If I had this matrix, I can think of the rows here as individual vectors. By the way, when we're doing determinants, we have to have square matrices to do them. We cannot do determinants on matrices that aren't square. So everything that we're going to be doing in this chapter will have square matrices to start with. But I can think of each of those rows as a vector. And if I think about how you plot vectors, if you've seen vectors before, this is stuff that you've done. And if you haven't seen vectors before, we'll do a little bit more with vectors, especially generally. All right. So as far as vectors go, I can treat the 3 as an x and the 1 as a y, and treat that as the endpoint of something that comes from the origin and goes out to the point 3, 1. And then the same idea with the -2, 5. So I have another one come out this way. All right. I should have drawn this a little bit farther down. Let's see if I can do that. All right. So anyway, one of the things that you can do with vectors is add them, and then you can also talk about the parallelogram that is defined by these two vectors. And what I mean by that is, if I take an exact copy of this bottom vector here and put it up here at this tip, that is not an exact copy. Don't spin it, don't stretch it, just shift it. And do the same thing over here, you see a parallelogram, right? So one of the things that we're going to do with the determinant function, in this particular case, is talk about the area of this particular parallelogram. Now, I did this for the 2 by 2 case, where I've got 2 vectors and make a parallelogram. This extends to as many dimensions as we would like. I can just draw that picture better. Okay? But in general, we think of this quantity that we're trying to compute as a volume. So area is a 2-dimensional volume. If I had a 3 by 3 matrix, I could do a similar thing with 3 vectors. So if I had, in 3 dimensions, if I had 1 vector and a second vector and a third vector, you could talk about doing something like this. Looks like that, ish. Roughly, you can kind of see the 3 dimensions there, I hope. My bad drawing, you never know. But I see this, what looks like a box, but the sides are slanty, probably, because they're parallelograms, general parallelograms rather than rectangles. We call that a parallelopiped. It's a very, very long word, I know. But this is an example of a Parallelopiped, parallelopiped.
I think we call it parallelopiped.
Piped? Yeah, I've heard that pronounced that way too. Either way is fine. I just like to conserve syllables. Okay. So a parallelepiped. So it's a solid that has parallelograms as its faces. And again, I can think about this being generated by three-dimensional vectors. And again, if I think about a square matrix, I can think about those as the individual rows of the matrix. Okay? So again, the function that I want associated with the matrix is, if I take the function and I apply it to the matrix, I want to get a number that somehow represents the volume of this shape. So again, you might get a 4-dimensional object or a 5-dimensional object, so whatever volume means in those respects is up for debate. But that's the idea. We're going to associate a quantity with these vectors, and the function that we're going to take of these vectors is whatever volume is generated by that particular set of vectors. Okay. I'm going to do most, if not all, of my drawings in 2 dimensions. Just as a quick side note, in the handout that I just gave you, every single one of the pictures is 2-dimensional, except the one that's labeled on page 163. The reason I mention that is the one that's on the bottom of page 164 is a 2-dimensional figure, not a 3-dimensional one. I know they got the little dashes in there, and it looks like it might be 3-dimensional. That is not a 3-dimensional picture. That is a 2-dimensional picture. The only 3-dimensional picture is the one that's on the page that's labeled 163. Okay. Well, they're going to talk about what that picture means here in a minute, I promise. But I just wanted to emphasize that that is not, the one that's on page 164 at the bottom, that is not a 3-dimensional picture. It's a 2-dimensional one. Okay. All right, so here's the idea. If you're thinking about a volume function, there's some specific properties that you want that function to have. For example, if I go back up to this one, if I change this vector, the 3, 1, say to 6, 2, what's that do to my picture? It's going to make the bottom one twice as long, right? Right? If I make it 6, 2 instead of 3, 1, what's that going to do to the area here? Double it, right? So notice that if this is one of the properties that we're going to want our determinant function to have. Again, if we think about it as a physical quantity, if I multiply a single row by a constant, that changes the volume, that changes the determinant by that constant. Okay? So the way they write it in that handout that I gave you is that if you have, they write their general matrices as row vectors. I think they use B's, and I'm going to emphasize the fact that I've got vectors by putting little hats on them. If I take a constant, and whatever, it doesn't matter what the constant is, and multiply just the ith row by C, I'm changing that one dimension, right? So all that does is stretch or shrink one of your vectors, right? So it should change the volume by that particular constant. So we use DET to denote the determinant function. If I do the determinant of a constant times a single row, that should be the constant times the determinant of the original matrix. So again, think of this as that what I wrote down was a specific example. If I multiplied that first row by 2, it doubled the area. Right? So we think about this being, if we think about this one being specific with the first row, and the constant being 2, if I multiply the first row by 2, it doubled the area. Think of the determinant as the area or volume function. Okay? this is certainly one property we would want a volume function to have, right? I'm changing the scale on one of my directions, so it changes the volume by that amount. Does that make sense? Okay. All right. Another property that we probably want this to have is a weird one, but this is where it goes back to the picture that I was just mentioning on page 164 here. All right, so let's see if I can reproduce this picture. All right, so first, let's say I have a V. Oops, I don't need a 1 here. Let's say I have a V here. The book is using B's, but that's okay. I want to make sure I want to use V. All right, if I have V, now we talked about how I could draw the parallelogram. We started with the vector over here, and then I made a copy over here. Well, I could have started with the vector here and made a copy back over here and just finished off a parallelogram, right? So I want to put my W over here first. Let me slant it a little bit. Then we my W here. So then I get a copy of W here and there. Agree with that? Okay. All right. If I had another vector, let's say x, here. I just put that in a bad spot, but that's okay. I could do the same thing. Let me change where my W is here. Like I said, I probably just put this in a bad spot. Put the copy of x here and finish off the parallelogram, right? All right, so let's see if I can finish off this picture and make it look like the picture that the handout that I gave you is much better for what we're about to do. All right, so what happens if I add the V and the W together? I did not make a very good picture. What happens if I add the V and W together? So one of the things that you'll notice with vectors is that's the sum of the two. All right. Now make that parallelogram with the x. So x is going this way. Like I said, I did not do a very good job drawing this picture. Nope, sure didn't. This picture sucks. I'm going to fix this. Let's do this. I'm going to use the picture that's in the book so I can tell you what's going on. Because my picture is bad. Really bad. Oops. That's not what I want. Oh, that'll work. Okay, so go back here. And you're working on it, I know. All right. All right. This is why I gave you the handout, because my drawing is awful. All right. Here's the idea again. So let's say I've got, zoom in a little bit more here. All right, so let's say we've got here's that V here. And here is the W. Okay? Here's the X. Okay? Notice that this part here, I'm going to shade it in first here with the red. This part here would be with the V and the W in that area, right? And then this part here would be with the v and the x, or I guess that's the v and the x, and the w and the x. Do we see that? If this is my v, this is my w, and this is my x that I had before. This is v and x together. This is w and x together. Okay. All right, so let me shade this now in blue. This blue one is v plus w. And here's my x again, right? Here and here. So if I shade in blue here, I have that parallelogram. So now the question is, except it goes all the way up here, that I didn't shade in very well. Now the question is, how does the red shaded area compare to the blue one? The total of the red shaded area, how does that compare to the blue one? They're equal, and why? Is this part here included in the blue?
No.
No. It's included in the red though, right? How about this part up here? Is this in the red? No, but it is in the blue, right? But what do we notice about this triangle and this triangle? It's the same, right? They're congruent, aren't they? So the area that's down here missed by the blue is gained up here by the blue. You see it? The area that's missed down here by the blue section is gained up here by a congruent area. Okay. So how does this translate to this? I should have just used the picture to start with instead of trying to draw it. Okay. How does this compare to matrices? Well, let's think about what happened. In the blue picture, we added the b or the v and the w together to get that bottom piece, right? But we didn't change the x, correct? So for matrices, that means that we've taken two rows. Write it this way. We've taken two rows and added the two rows together. So I'll say B1 plus C1, or not 1, I. We've taken two vectors and added them together, right? But only two of them, not all of them, correct? Okay. So these two are these two have been added together. We want to be able to split that into two pieces. This is the same as the determinant of B1, B2, Bi, Bn, plus the determinant of B1, B2, Ci, Bn. Okay, the important thing here to notice is that we have not added two matrices together. We've added two rows together, right? The matrices are identical otherwise, okay? So this is not saying that the determinant of a matrix plus another matrix is the determinant of each matrix and added together, okay? These matrices are identical except for the ith row. And all we've added together is the ith row. But again, that's the idea, is all we're trying to do is play with one of the dimensions, right? What happens to the determinant? What happens to the volume if we play with one of the dimensions, just like we did with the constant in times the particular row, right? All right, well, let's think about another property. What would happen? What do you think should happen to the volume if I take one vector, one row, and the other one landed right directly on top of it? What should happen to the volume? Think about it in two dimensions. If I take one vector and put another one right on top of it, how much area is going to be determined by those two vectors? 0, right? So if I have two vectors that are pointing exactly the same way, that are the same vector, that kills a dimension off, right? Now, if I kill a dimension off, I kill the volume. Think about it in 3 dimensions, right? What's the volume of, say, a rectangle in 3 dimensions? It has no height, so it would be 0, right? If I kill off a dimension, I get 0. So if, in general, we have a determinant of a B1, a BI, and then I go down and I see the same vector again in the ith row, that determinant is going to be 0. So the B is supposed to be the same BI. If you have a repeated row, that tells you the two vectors are giving you the same information, right? You lost a dimension, so you killed your volume. That makes sense, right? If I take 2 and smack it, we'll take 1 and smack it right on top of the other, I lose my volume. Box with no height, square with no width, right? Rectangle with no width, those kinds of things. All right, this is actually enough, almost enough, to compute the determinant of anything that you would like, except for the fact I have no scale. I have no unit, right? So the last thing we need is a unit. And the unit we probably are going to use is the determinant of the identity matrix. Think about what the identity matrix looks like. The 2 by 2 identity matrix would be 1, 0, 0, 1. What kind of a shape would be determined by the vectors 1, 0, and 0, 1? A square. And specifically, what would the length of each side of that square be? 1. So its area would be 1, right? If I did 1, 0, 0, 0, 1, 0, 0, 0, 1 for 3 dimensions, what shape would I get? A cube, and its volume would also be 1, right? So what do you think the determinant of the identity matrix is going to be? 1. Good. Cool. This is enough to make a determinant function. This is enough to be able to calculate the determinant of any matrix, all motivated by volume. So, as a definition, this is in that handout I gave you. This is definition. Nope. Where is it? Oh yeah, it's definition 4.1.1. It's on page 166. So it says a function that satisfies it says it gives you different axioms. So the axiom L is what it refers to as the linearity axiom, which is linear in the row. And then the S is your scale, which is giving you, the S is the 2 rows are identical, and the N is your scale. So that satisfies, let me give this a name. I'm going to call it the function DET. That satisfies, the first property is of the determinant of B1. I'm going to say C1 BI plus C2 CI down to Bn is I take out the first one and I split it up over the sum, which is a 1. The reason why this is referred to as a linearity axiom, a linearity property, is that anything that splits up in this fashion is referred to as a linear property. So it's linear in the ith row. So we've combined the constant multiple and adding two rows together in one axiom. So all we're doing is splitting up at the plus sign and factoring out the constants. That's what it means to be linear in a particular spot. Again, notice that we have not changed any other part of the matrix. The only thing that's been changed from one to the other is the ith row. The rest of the matrix is identical. The second property is that if you've got a repeated row, write this a little better, B1 to BI to BI to BN. If you have a repeated row, the determinant is 0. It kills the dimension. And the third one is that the determinant of the identity matrix is 0, or no, it's not 0, is 1. Any function that satisfies this is called a determinant function. So they actually asked a series of questions after this definition in that handout that I gave you. The questions that they ask are, number one, now that we've defined properties that we want, is there actually a function that satisfies these things? Do we actually even have a function that does satisfy these properties for matrices? Well, it'd be a really stupid thing to talk about if the answer to that weren't yes. Okay? Okay. The second thing is, if we find a function, is it unique? Is there only one determinant function? Notice that I said that a function that satisfies these properties is called a determinant function. Well, the fact that it says determinant makes you think of the word determined. What do you think about uniqueness? Do you think there's only one? Given just given the name that's given to the whole function. Determinant, determined, right? You think there's more than one? No. There's going to be more than one way to compute it. There are multiple ways to compute it, but it's the same answer every time. So no, it will be unique. Okay? So if we were going to go through all of this, we would need to prove an existence and uniqueness. Now we'll talk about existence because we'll actually talk about how to compute determinants, but I'm not going to spend class time on the uniqueness part because it's a little bit harder to prove. Not impossible, it's not bad, but there is a unique determinant function. There is, in that case, it's the determinant function for a matrix. All right. Well, let's look at this property a little bit and see if we can relate it back to stuff that we've already talked about. We're talking about looking at operations on individual rows at a time, and we're given the value of the determinant of an identity matrix, or value of a determinant where we have two rows that are the same. What property have we talked about with matrices, doing things to matrices, do you think is going to help us apply one way to figure out determinants? What stuff have we done where we've put rows together and those kinds of things? Yeah, reduce row echelon form, right? If we can row reduce a matrix, we can probably figure out its determinant, right? Okay? So let's see if we can do that. All right. So let's go back up to that first example. 3, 1, negative 2, 5 was what I gave you, right? Okay. If I want to row reduce this, the first thing I want to do is get what? I need a 1 in the 3 position. Now I'm going to be a little bit clever here. I'm going to take row 2 and add it to row 1 to do that. Okay. If we do row 2 plus row 1 replace row 1, I get 1, 6, negative 2, 5. This kept me from having to do a fraction. Now let's think about what, I know we did a row operation to get to this point, but let's think about how the determinant of these two matrices was comparing with each other. I took -2, 5, and added to this one. So notice that this row stayed the same, right? So that looks like one of those properties where it stayed the same. Let's figure out how we got the 1, 6. Well, this matrix I can look at as this and this, and put them together by doing what? If I look at those two matrices, back relative to how we defined what properties we wanted for our determinant function, how would we put these two together to give me this matrix? Add which one? Add what? The first rows, right? Remember, we only do things a row at a time with that determinant operation, correct? Okay. We're not adding these two matrices together, right? We're only adding the two rows and keeping the two first rows together and keeping the second row the same. Okay? So let's see. What's the determinant of this matrix here?
0.
0, right? This one has a determinant of 0 because the rows are the same, right? This matrix, so that means that this matrix here has the same determinant as the original one we started with. Okay? So we didn't change the determinant at all. Because all I did was take the first two rows, add them together, but in that second matrix, the two rows were identical. So it doesn't change the determinant at all. All right, so we got a 1 up in that upper left-hand corner. What's the next thing we want to get? 0 below it, right? So I need to take 2. What just happened? There we go. We're going to do 2 times row 1 added to row 2, replace row 2, which gets us to 1, 6 here, and then 0 and 17 there. Now notice again, row 1 is not affected at all by this, right? So we have identical rows. But let's again think about how we got to this point. We did 2 times row 1 added to row 2, and we didn't change row 1, right? So one of the rows we had would be 1, 6, -2, 5. Another one we would have here would be, let's see. Make sure I do this right. Because it's these two rows that I need to add together. So I have 1, 6 here, and then we would have had 2, 12 here to get to that point, right? And add rows 2 together. Row 1 is unchanged. Row 2 we add together to get to that point. We see that? Okay. This matrix is what we started with, right? Okay. How about the determinant of this one? Can you tell me what the determinant of that second one is?
Still 0.
Why is it 0? You're right.
The second one is just a multiple of the first.
Yeah, good. Go ahead.
So it would say it would be like 2 times 0.
Yeah, so this second row is 2 times the first one, right? So if I look at compare this one to this would be 2 times the determinant, right? But what is the determinant of this one at the bottom? 0. 2 times that would still be 0, right? So again, if I go from here to here, the determinant is unchanged. And notice that anytime we have that elementary row operation where we take a multiple of one row, add it to a second row, and replace the second row, it's not going to change the determinant at all. It'll never change the determinant. Okay? The reason for that is why? We leave the row that we're playing with alone, correct? And in the second matrix, we're going to do the constant multiple of that same row and put it in the row that we're adding to. If I do the constant multiple of this row and put it down here, I get a matrix that has two rows that are essentially identical. So that determinant is always going to be 0, and this is the matrix you started with. So anytime you do an elementary row operation that adds the row, adds a multiple of one row to another and replaces the other, you don't change the determinant. Okay? Cool, right? Okay? So that particular elementary row operation doesn't change anything. Now I've got to work with this 17. Let me just rewrite this down here. 1, 6, 0, 17. The next row operation would be to do what? Good. Run 17 times row 2, replace row 2. That definitely should change the determinant, right? Because we're doing a constant times a row. All right, I'm going to think about it backwards. If I went from here to here, if I went from this one on the right to this one on the left, how many times larger should the determinant of this one on the left be than the one on the right? 17, right? We agree? Okay. So this determinant is 17 times this determinant. Does that make sense? And now you can do the last one. We know what that operation is. That's negative 6 row 2 plus row 1 replace row 1. What does that do to the determinant? Nothing. And what is this determinant equal to then? 1. So what's the determinant of the original matrix have to be? 17. Good. Now, in this particular example, there are other ways to do determinants, by the way. This is not the fast way to do determinant for 2 by 2. If you've seen it before, you know how to do it. But I want to do this with illustration because, in general, the bigger the matrix gets, determinant with row operations is pretty much the fastest way to do it. But notice that we got to this determinant just by doing 2 elementary row operations. Constant times a row and constant times a row added to a second row plus a second row. I didn't do a row swap, right? And notice the row swap wasn't included in the original definition for determinant. One of the reasons why is we can figure out what the determinant of a row swap has to be. Okay? So let's say we were here. You can do a row swap without actually swapping rows. We can do row swap by adding rows together and doing constant multiple. So the first thing I'm going to do is take row 2, add it to row 1, replace row 1. What does that do to the determinant? Nothing, right? There's absolutely nothing to do to the determinant. Next thing I'm going to do is negative row 1 added to row 2, replace row 2. What does that do to the determinant? Nothing again, right? Remember when we do the elementary row operation, that's constant times one row added to second row, replace second row, doesn't do anything to the determinant at all. Okay? It's a little strange, but that's the properties of the determinant, right? We already showed that. Let me now add row 2 to row 1 and replace row 1. What did that do to the determinant? Nothing. And I'm really darn close to a row swap, right? Without having actually done a row swap. The last thing I need to do, however, is what? I gotta take row 2 times -1. Good. Now that does change the determinant, doesn't it? What does it change the determinant by? It just changes the negative, multiplies it by -1. That's the other property, isn't it? So if you do a row swap, it negates the determinant. It makes it negative. If it was negative, it makes it positive. If it's positive, it makes it negative. So this row operation flips the sign of the determinant. Okay. Wish I had time to do a bigger example, but I've got about 2 minutes, and I don't think I want to do the example. One thing I will mention, though, is the following. By the way, if you see vertical bars around a matrix, it tells us to do the determinant. Say you want to do this determinant. Now, one of the reasons why I wrote it this way is because it's triangular. This is upper triangular. We talked about that. That's for the test, right? All of the non-zero entries are above the main diagonal. Think about what you would do if you were going to row reduce this farther. I'd need to make that a 1, right? I need to make that a 1, need to make that a 1, need to make that a 1. Those are all constants, and those change the determinant, correct? But if I make all of these zeros, you're going to use the same type of row operation, right? That's not going to change the determinant, correct? So the only thing that matters for the determinant are these constants. So when we have it triangular, the only thing that matters are these constants here. Because when we do the other operation to make these all zeros, it doesn't affect the determinant, right? Because you're going to do a multiple of one row added to the other. So for a triangular matrix, the determinant's easy. I just need to multiply down the diagonal and get the determinant. And if you like, with what we talked about, you can think about it as just popping out the constants, right? I pull this 2 out to make it a 1. I pull this 3 out to make it a 1, this -1 out to make it a 1, and that 4 out to make it a 1. So they do the determinant for a triangular matrix. We can just multiply down the diagonal and give us the determinant. So notice that you don't even have to go through a full-blown Gauss-Jordan idea to get down to how to figure out the determinant. I just need to get it triangular. As soon as it's triangular, I can multiply down the diagonal. So next time, we're going to do some more examples of doing these by row reduction. I'm going to have a video for you tomorrow to show you a second way to calculate determinants. It's called expansion by minors. Okay. So we'll have 2 different ways to do it, and we'll do more examples next time. So have a good one. We'll see you then.